final skill in lesson 0-4 is being able to simplify expressions in exponent form. So now we're going to talk about how do we turn radicals into exponents, which are much more friendly and easier to work with. But that means you also have to know your exponent rules, and your exponent rules that you need to know are your product rules, your quotient rule, and your power rule. So we've been using these, but your product rule simply says if you have x to the n times x to the m, it's equal to x to the n plus m. If you have x to the y divided by, oops, I don't want to really use y. X to the a divided by x to the b, it's equal to x to the a minus b. I can use whatever I want for those buggers here. And the power rule says power to power, so if I have x to the a raised to the b is equal to x to the a times b. So we're going to convert these radicals into exponent rules so that we have some flexibility working with them. Now they give a little bit of an explanation here about all this, and you can read through that and see how you understand, but basically they're giving you a pretty good explanation of what's going on there. I'm going to highlight then some applications of these exponent forms. So in essence what they're telling us in this key concept is if we have b to the 1 over n, the bottom number, the denominator, always tells us the index of our radical. And then the b is simply our radicand. So the b goes inside here, which is our radicand that we got from our previous page or two. So when we look at these, always think of this bottom number on your exponent as being the index of your radical. But there's one more step to this. They say, well, what happens when you have b to the m over n? You don't change anything. N still remains your index of your radicand. It's still b, but you can think of it one of two ways, and here's where you have some flexibility. The second form says it's b to the m, but typically that's not the easiest way to do it. The easiest way would be to first find the radical of b and then take that expression and raise it to the m power. Okay, so we have the flexibility of putting the m with the b and then taking the nth root, or taking the nth root of the b and then raising it to the m. So how can we apply this to simplified expressions with rational exponents? So let's take a look at that first example. And I apologize, those exponents are really small, and I noticed that I read the wrong exponent on the previous example. But what we're going to be looking for are common bases here. This 32 and the 2 have a common base, and we want to convert them into a common base. So here's my thought process. We want the 10th root of 32. Well, 32 can be thought of as 2 to the, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I'm going to think of it as 2 to the 5th over, and then this is going to be the 6th root of 2. Now, we want to now come back and say, well, let's take a look at using these exponent rules. So I'm going to convert this into, rather than the 10th root of 2 to the 5th, I'm going to write it as 2 to the 5th over 10. Now remember, the bottom number always told us what the index was, and the 5 told us what the power of the radicand was, which really means we have 2 to the 1/2 power. On the bottom, I'm going to think of this as 2 to the, this is a 1 here, so the 1/6. So this is 2.5 over 2 to the 1/6. Now here we come back with our product, quotient, and power rules. We're going to apply our quotient rule here. The same bases are being divided, so anytime your bases, same bases are being divided, you subtract exponents. So it's 1/2 minus 1/6. So in order to subtract, you're going to get a common denominator, make the 2 a 3 by multiplying, multiply by 3 to make it a 6. So it's 3/6, so 1/2 is 3/6, which is equal to 2. Now we got 3 minus 1 is 2 to the 2/6, which means it's 2 to the 1/3, so really we can rewrite the final answer as the cube root of 2. That's our final result in simplest form. Okay, so let's take a look at another example of using these exponents. We have the 4th root of x to the 21 y to the 15. And I've already demonstrated a little bit of this flexibility, I think, with this, because we're going to look at this as, x to the 21st times y to the 15th raised to the 1/4. So I can think of that then, using your power rule, x to the 21/4 times y to the 15/4. And now I can reduce these. So I want to think of this as, and you got lots of flexibility here, and as I was doing this I thought of probably another way that we can do the same thing. This is x to the, I want to see if I can get any clean powers of 4 either, and I can go 20 over 4 times x. That would be the same thing as x to the 1/4, x to the 21/4, then times y to the, I want to take out as many powers of 4 in this one as well. So 4 going to 15, 12 times, so 12/4 times y to the 3/4. Okay, so now x to the 24th is the same thing as x to the 5th. Y to the 12/4 is y to the 3rd. Now these two are both 4th roots, and they don't simplify any further, so I'm going to convert it back into the 4th root of x to the 1st and y to the 3rd. So simplest form. Let's see. If I check out, okay, we're fine. Because I was looking for, we had an even root here of 4, but we didn't have even powers here, so I don't have to worry about absolute values. And finally, taking a look at this one, they both have a base of 16, so I might just stay with that base of 16. And it says we've got a base 16, we're dividing, so let's use our quotient rule. It says we should have 16 to the 3/4 minus 1/4. Then that's 16 to the 3 minus 1, okay, that's 2/4, which is 16 to the 1/2. But 16 to the 1/2 is the same thing as the square root of 16, which, if we want to reduce, is just 4. The principal square root is 4. So gave you a few different examples there to look at, and different strategies to solve those using exponent rules.